Welcome back to the Sense Check Lab. We're so glad you're joining us today. Here we explore the facts, myths, and science behind the choices we make every day. Settle in and get ready for another deep dive where we put the latest trends and topics under the microscope. Let's make sense of it together. Today we're diving into something you probably interact with constantly: plastics. Think about the water bottle you carry, maybe the containers your food is stored in, or even products for babies and young children. Plastic safety? Well, it's a pretty significant topic, and we've all seen those BPA-free labels, right? They're everywhere. They're supposed to reassure us, promise a safer option. But here's the crucial question, the thing we really want to get into today. Are they truly safer, or have we simply swapped one chemical concern for another? Let's try and unpack this. So, to start us off, maybe let's just establish what exactly BPA is.
Right. So bisphenol A, or BPA as most people know it, it's um it's an industrial chemical that's been very widely used for a long time. It's a type of endocrine disrupting chemical, an EDC. That means it can basically mess with our body's natural hormones.
Yeah.
You find it, or you used to find it extensively, in those hard, clear polycarbonate plastics. Think water cooler jugs, reusable drink bottles, and also in epoxy resins, which line the inside of many food and beverage cans, plus plastic packaging, dental sealants. It was quite pervasive.
Okay, I know there's been a huge amount of public concern about it for years now. What was the science that really ignited those worries?
Yeah, the main concern stems from its ability to leach out, to migrate from the plastic or the resin into our food and drinks. And studies consistently showed it was incredibly widespread, like detectable in the urine of almost everyone in the U.S. population, maybe at low levels, but still there. What's really striking, though, is how it works. BPA has been shown to mimic estrogen, one of our body's own natural hormones.
So it pretends to be estrogen.
Exactly. Hormone mimicry. And that raises really important questions about its health impacts. Research started linking BPA exposure to a pretty wide range of issues, things like reproductive problems like reduced fertility, changes in embryonic development, but also impacts on metabolism, potential links to insulin resistance, type 2 diabetes, and associations with cardiovascular disease, asthma, liver issues, even things like ADHD. And what's particularly concerning and really important to grasp is that these effects weren't just seen at high doses, they were observed at very low doses too.
That's a critical point. Not just huge exposures, but even tiny amounts could potentially have an effect.
Right.
So what did regulators do once the science became clearer?
Well, given these mounting concerns, regulatory bodies around the world did start taking action. It wasn't overnight, but things happened. The European Commission, for instance, banned BPA in polycarbonate baby bottles back in 2011. Then later, by 2018, they banned it in all plastic bottles and packaging meant for babies and kids under 3. And just recently, in December 2024, the EU adopted a much broader ban: no BPA in any food contact materials. That's a big step. We saw similar actions elsewhere too. South Africa banned it in baby bottles. Japan actually started phasing it out of thermal receipt paper way back in 2001.
Okay, so the world starts banning BPA. And naturally, manufacturers respond. The market just seemed to explode with BPA-free options. They certainly sounded reassuring, but was this really the fix everyone hoped for? How did manufacturers adapt?
They adapted quickly, absolutely. Companies started producing reusable bottles from metal or different types of non-polycarbonate plastics, all prominently labeled BPA-free. You know, Nalgene switched to bottles made from something called Triton copolyester. SIG, the aluminum bottle company, developed a new lining called EcoCare, marketed as completely BPA-free.
Right. And what exactly were these new BPA-free things made of? Were they truly safer, or was it just, well, a different chemical with maybe a similar problem?
That's where the story gets a bit more complicated. Many of these alternatives simply introduce substitute chemicals, often other bisphenols like bisphenol S, BPS, or bisphenol F, BPF. It's key to remember, BPA is just one member of a whole family of bisphenol chemicals. There are at least 16 different ones. BPS, for example, became a really common replacement, especially in things like that thermal receipt paper we mentioned. And the research, well, it suggests that BPS has estrogenic activity, very similar to BPA. It acts like estrogen too. And then there are other chemicals like triphenyl phosphate, TPP, that also started showing up in BPA-free products. Some studies found TPP might even be more estrogenic than BPA.
More estrogenic. Wow. Okay, so the label didn't necessarily tell the whole story.
Exactly. It highlights a potential gap between, the marketing claim BPA-free means safe and the actual science behind the replacement chemicals.
So for someone trying to make the right choice, it feels like a bit of a moving target. BPA-free didn't automatically mean free of hormone disruptors. I think I also heard about EA-free labels at some point. Was that any better? Estrogenic activity-free.
Yeah, exactly. As evidence grew about the potential dangers in some BPA-free plastics, we did see the introduction of EA-free labels, estrogenic activity-free. And while that sounds like a definite improvement, it hasn't always, shall we say, translated perfectly to improved quality standards and practice. For instance, Eastman Chemical, the makers of Triton, marketed it as EA-free. But some independent third-party testing actually found it did release other chemicals with estrogenic activity under certain conditions, like UV exposure. It just
Huh.
highlights this real challenge. Sometimes manufacturers conduct their own studies, or there are legal challenges against conflicting scientific findings. Independent verification becomes absolutely crucial.
It really makes you question what's behind the label. Okay, let's dig into that independent research then. What did scientists find when they actually put these BPA-free products and the older ones to the test?
Well, there was a key study back in 2011 that specifically looked at BPA leaching from different reusable water bottles. They confirmed that the traditional polycarbonate bottles did leach detectable BPA at room temperature. And importantly, heating the water, like putting hot tea in them, significantly increased how much leached out.
Okay, that makes sense. Heat increases leaching.
But what was really eye-opening were the results for some of the so-called alternatives. Aluminum bottles lined with certain types of epoxy resins, remember, epoxy resins often contain DGA. BPA showed really variable BPA leaching. And crucially, boiling water in these epoxy-lined bottles dramatically increased BPA migration, like more than a four-fold increase in the release rate. Even more worrying, one particular discount brand of epoxy-lined aluminum bottle leached way more BPA than even the old SIG epoxy-lined bottles, and actually 5 times more than the standard polycarbonate bottles, just sitting there at room temperature.
Wait, seriously, some BPA-free labeled aluminum bottles were leaching more BPA than the original plastic ones they were meant to replace.
Under certain conditions, yes. It strongly indicated that unknown factors in the manufacturing process itself played a huge role in how stable that lining was and how much BPA could come out.
That's that's genuinely surprising. It completely flips the script on what most of us probably assumed.
Yeah.
But were there any options identified in that study that were genuinely BPA-free, that didn't leach it?
Yes, absolutely.
Uh,
Despite those problematic examples, the study did identify options where no detectable BPA contamination was found. This included water stored in bottles made from that Triton copolyester plastic we mentioned earlier,
Okay.
uncoated stainless steel bottles, and also aluminum bottles that used SIG's newer EcoCare lining. So those materials were deemed suitable for use without BPA contamination, provided they were used according to the manufacturer's recommendations.
Okay, so stainless steel, Triton, and that specific SIG lining looked good in that study. But even as we're focusing on BPA and its direct replacements like BPS, the research seems to show we're swimming in a whole soup of other chemicals in plastics, right? Beyond bisphenols, what other harmful things should we maybe be aware of?
That's a really essential point. Plastics aren't just one thing. They contain literally thousands of different chemicals, additives, processing aids, residual monomers, and often their presence isn't disclosed on any label. So beyond the bisphenols, some major groups of concern include
Phthalates.
relatants, right? Heard of those?
Yeah, they're commonly used to make plastics flexible. Think PVC, vinyl flooring, some food wrap, even personal care products. They're also really widespread, commonly found in human urine and blood samples, and they've been linked to, well, a range of issues. Abnormal development, problems with male and female reproductive health, things like decreased sperm quality, pregnancy loss, and even respiratory problems like asthma.
Okay, phthalates. What
And then
else?
there's PFAS, the forever chemical.
Oh, yes, those have been in the news a lot. And for good reason. PFAS stands for per and polyfluoroalkyl substances. It's a huge group, over 10,000 different man-made chemicals. They've been used since the 1940s because they're incredibly good at repelling oil and water and resisting heat. Think non-stick cookware, grease-resistant food packaging like pizza boxes or microwave popcorn bags, stain-resistant carpets, waterproof clothing, even some cosmetics and firefighting foam. The huge concern is that they break down extremely slowly in the environment and in our bodies, hence forever chemicals. They accumulate over time.
Accumulate where?
Everywhere, basically. Drinking water, soil, food, especially things like fish and dairy, even in household dust. Studies show most people in industrialized nations have detectable levels of PFAS in their blood, and they're linked to a growing list of health concerns. Decreased fertility, increased high blood pressure during pregnancy, developmental delays or effects in children like low birth weight or behavioral changes, increased risk of certain cancers, kidney, testicular prostate, and they can also interfere with our immune system function and natural hormones.
That's quite a list. Forever chemicals. Anything else?
Well, even heavy metals can sometimes be an issue. For example, antimony, which is used as a catalyst in making PE plastic, the kind used for most single-use water bottles. Studies show antimony can leach out, especially if the bottles are exposed to heat, like being left in a hot car. High levels could potentially cause nausea, vomiting, diarrhea.
Okay. And then there's the whole issue of the plastic breaking down itself, right? Microplastics.
Exactly. Microplastics and nanoplastics. This is maybe the most pervasive and complex issue of all. See, plastics don't biodegrade like organic matter. They just break down into smaller and smaller pieces. First, microplastics, which are tiny fragments, fibers, beads. Then even smaller nanoplastics, which are microscopic. And they are literally everywhere now. Oceans, rivers, soil, air, even found in remote Arctic ice. And believe it or not, in clouds.
In clouds, wow.
Yeah. So we inevitably ingest them and inhale them. Through tap water, bottled water, which often contains more than tap water, beer, honey, salt, seafood. The list goes on. They're also in the air we breathe, from synthetic textiles, tire wear, etc. And the really small particles, especially nanoplastics, well, they might not just pass through us. Particles under about 150 micrometers can potentially be absorbed by our tissues and organs. They've been found in lymph nodes, liver tissue, brain tissue, tests, blood, even placentas. Nanoplastics might even be able to cross the blood-brain barrier and the placental barrier.
That's deeply unsettling. And what are the risks once they're inside us?
Well, the risks are still being heavily researched, but they seem to fall into a few categories. There's the physical or mechanical risk, potential irritation or blockage in organs, especially the digestive tract for larger particles. Then there's the chemical toxicity, both from the plastic polymer itself. Some building blocks, like those in PVC or polyurethane, are inherently more toxic, and also from the chemical additives within the plastic, like sialates or flame retardants, leaching out. And third, microplastics act like little sponges in the environment. They can absorb other pollutants from the water or soil, things like persistent organic pollutants, POPs, pesticides, heavy metals, and then potentially transport these toxins into our bodies when we ingest the plastic particles. Some types of plastic, like polyethylene and polypropylene, seem to be particularly good at accumulating these other pollutants.
So it's the plastic itself, the chemicals in it, and the chemicals it picks up. A triple threat, almost. And you mentioned recycling earlier. Can that make things worse sometimes?
It certainly can, if it's not done properly or if there isn't good oversight. Recycling is crucial, but it has potential pitfalls. For example, black plastic. It's hard to sort automatically, so sometimes it includes plastic recycled from electronics waste, which can contain high levels of brominated flame retardants, chemicals we know are harmful. There have been documented cases where this contaminated black plastic has ended up being recycled into things like kitchen utensils, coffee cup lids, takeout containers, even children's toys, especially in regions where regulations might be looser.
Oh, wow. So your recycled spatula could have flame retardants from an old computer casing.
It's a possibility, unfortunately. And then there's incineration, or waste to energy. While it gets rid of the bulk plastic, burning it releases fine particulate matter into the air, which is linked to lung and heart disease. It can also release heavy metals like lead and mercury, and highly toxic chemicals like dioxins and furans, which can harm the immune, reproductive, and nervous systems. So disposal methods have their own sets of problems, too.
It really feels like a complex web. Okay, so given all this research, what are the major regulatory bodies like the FDA or EFSA in Europe saying now? And what are the big debates still happening among scientists?
Well, agencies like the European Food Safety Authority, BPA-Free, are definitely active. They continuously review the safety of chemicals used in food packaging. And as we said, EFSA's updated risk assessment on BPA was a key driver behind that recent, really comprehensive EU ban on BPA in all food contact materials. So regulation is happening, sometimes driven by new science.
But it sounds like it often lags behind.
It often does, yes. And there are significant challenges. Take PFAS, for example. We know there are thousands of different PFAS chemicals. But most regulations and even most research studies still focus on only a handful of the older, better-known ones, like PFOA and PFOS. As those get phased out, companies often just swap them for slightly different, less studied PFAS chemicals, which might have similar properties and potentially similar health risks. It's a bit like whack-a-mole.
Right, the regrettable substitution problem.
Yeah, exactly. And underpinning a lot of this is a significant lack of transparency from the chemical and plastics industry. It's often very difficult for researchers, regulators, and certainly consumers to know exactly which chemicals are present in a particular plastic product. Trade secrets are often cited.
So it's just incredibly hard to get a complete picture of the potential risks. And I imagine the industry often points to the complexity, saying the data is inconclusive. How do scientists navigate that?
Precisely. Scientists are definitely grappling with the sheer complexity. Thousands of chemicals interacting in unknown ways. But microplastics themselves vary hugely: size, shape, polymer type, the additives they contain, the pollutants they've picked up. This makes it genuinely challenging to draw direct, clear-cut causal lines between exposure to a specific plastic chemical or microplastic type and a specific health outcome in humans. It's not like a simple bacteria causes disease link. So yes, the industry often highlights this complexity and the lack of definitive proof of harm for many substances. But many scientists and public health advocates argue for applying the precautionary principle.
The precautionary principle.
Yeah, the idea that when there's credible scientific evidence suggesting potential harm to human health or the environment, we should take protective measures, even if the cause and effect relationship isn't fully, incontrovertibly established yet. The argument is, let's not wait potentially decades for absolute proof, especially with substances that accumulate in our bodies and the environment. By then, the damage could be widespread and irreversible.
So act now based on the warning signs, rather than wait for disaster.
That's the essence of it. There's also a huge push within the scientific community for developing standardized methods for studying microplastics, how to sample them, how to identify them, how to measure them consistently. That would allow for better comparison between studies and build a more robust evidence base faster.
Okay, this has been incredibly illuminating, if also a bit overwhelming. It touches everything. So let's bring it back to the listener. For us, as individuals navigating this plastic world, what are some practical things we can actually do to reduce our exposure?
It's a great question because while individual actions alone won't solve the whole systemic plastic pollution and chemical exposure problem, there absolutely are practical steps you can take to significantly lower your personal exposure. First, try to reduce direct contact between plastic and your food and drinks, especially when things are hot. Heat is a major factor in leaching.
So definitely no microwaving food in plastic containers.
Definitely not. Transfer food to glass or ceramic before heating. And if you still use older polycarbonate bottles or those potentially iffy epoxy-lined aluminum ones, avoid putting hot liquids like coffee or tea in them. Use them only for cold drinks. Second, be critical of those labels. Remember that BPA-free doesn't automatically mean risk-free or chemical-free.
Yeah.
As we discussed, alternatives like BPS or TPP might have similar or maybe even worse estrogenic activity. And even EA-free labels warrant some caution, as independent testing has sometimes found otherwise.
Right, don't just trust the label blindly.
Exactly. Third, think about those thermal paper receipts. They often contain BPS. Try to minimize how much you handle them, maybe decline receipts you don't need. And definitely wash your hands after handling them, especially before eating. Avoid keeping them crumpled up in purses or wallets where the dust can potentially contaminate other things like money or even snacks.
Good tip about receipts. What about choosing different products altogether?
Yes, opting for alternatives is probably the most effective strategy where feasible. Glass is an excellent choice for water bottles and food storage containers. It's inert, doesn't leach chemicals. Even something like Pyrex containers with plastic lids are generally considered a much better option than all plastic containers, as the main food contact surface is glass.
Okay, glass is good. What else?
Stainless steel is generally a very good alternative, especially for water bottles and lunch containers. It's durable, doesn't break easily, and is considered very safe regarding leaching, even with hot liquids. Just make sure it's food-grade stainless steel. Ceramics are also great for food storage and tableware. Again, very stable.
So, glass, stainless steel, ceramics, those seem like the go-to safer materials. But what about microplastics? You said they're everywhere. They seem almost impossible to avoid entirely.
They are incredibly challenging, yes. Because they're so widespread now in our water, food, and the air we breathe, completely avoiding them is probably unrealistic for most people. But being aware of the major sources can still help inform choices. For example, knowing that bottled water often contains significantly more microplastics than tap water might make you reconsider your reliance on bottled water. Maybe invest in a good water filter for your tap water instead.
That makes sense. Filtering tap water might be better than bottled.
It could be, yes, depending on the filter type and your local water quality, of course. Choosing whole, unprocessed foods over highly processed ones might also help reduce exposure, as processing can introduce plastic contamination. Reducing dust in your home through regular vacuuming with a HEPA filter could help reduce inhalation exposure. But ultimately, you're right, individual actions for microplastics have limits. The biggest changes really need to come from upstream, better product design, phasing out problematic plastics and additives, improved manufacturing processes, and much, much better waste management and pollution control policies globally. Individual awareness, though, is that crucial first step towards demanding those bigger changes.
Okay, pulling all of this together then. After this deep dive, what's the main takeaway message you want people to leave with?
I think the biggest takeaway is that the simple BPA-free label isn't the end of the story. It doesn't automatically equate to safe or risk-free. The chemical landscape of the plastics we use every day is incredibly complex. We've talked about BPA substitutes like BPS, but also phthalates, PFAS, heavy metals, many raising significant health concerns, potentially impacting our hormones, our development, our metabolism, even possibly increasing cancer risks. And layered on top of all that, we have the pervasive issue of microplastics and nanoplastics. They're already in our environment, they're already in our bodies, and the long-term consequences are still largely unknown, which is worrying in itself.
It definitely raises a really important question for all of us, for you listening right now. In this world that's so saturated with plastic, how do we find that balance? The balance between the undeniable convenience plastics offer and these potential, perhaps serious long-term health implications. Do we wait for that absolute undeniable proof of harm for every single chemical, which, as you said, could take decades? Or do we act now, demanding more rigorous testing, more transparency from manufacturers, and supporting policies that aim to protect public health based on the precautionary principle?
Yeah, I think we really encourage you to think critically. Look beyond the simple marketing claims on labels. Make informed choices about the products you buy and use where you can. Opt for those safer alternatives like glass and stainless steel when it's practical for you. And perhaps consider supporting broader efforts, policies aimed at reducing chemical exposures at a population level, pushing for greater industry transparency about what's actually in these products that surround us.
Thank you so much for breaking all that down for us. It's a lot to think about, but really crucial information. And thank you for joining us here at the Sense Check Lab. If you enjoyed this deep dive, don't forget to subscribe and maybe share it with your friends or family who might find it useful. We really appreciate your support and look forward to checking in with you next time for more thoughtful conversations and hopefully some more sense making. Until then, take care.